Video 30, Master Course, Quantum Chemistry of Molecular Electromagnetic Properties. The topic of this lecture is quantum mechanical expressions for the polarizability. In the last chapter, we arrived at two expressions for components of the electric dipole polarizability. One was as the second derivative of the energy in the presence of an electric field, and the other one was as the first derivative of a component of the electric field dependent electric dipole moment. And we can use both expressions in order to obtain quantum mechanical expressions for components of the dipole polarizability. So let's start with the derivative of the energy. Now again, in the same way as when we looked at quantum mechanical expressions for the dipole moment, we can use the expressions for the energy in the presence of the field, which we have from perturbation theory. And just then take derivatives of this expansion of the energy in perturbation corrections. Now, since the polarizability is defined as the second derivative of the energy with respect to components of an electric field, evaluated at zero field strength, the only term which actually survives taking the derivatives is the second order correction to the energy. Because the first order correction only depends linear on the field, so if you take the second derivative, this goes away. And all the higher order corrections, third order, fourth order energy corrections, they will become zero if you evaluate the derivative at zero field strength. So only the term which actually is quadratic in the field will survive, and that's the second order energy correction. Now in chapter 3 of the book, we derived expression for the second order energy correction as a sum over excited states of the molecule, where we had here the energy difference between the unperturbed energy of the ground state and the excited states, and we had transition moments from the ground state here to the excited state with the perturbation operator. So it's this expression from which we now have to take second derivatives. Now if you want to do that now, you have to look at which of the terms in this sum of states expression actually depends on the field. These are the unperturbed wave functions for the ground state and excited state, so they are field independent. These are also the unperturbed energies, so they're also field independent of the field. So the only thing which actually depends on the field are our first order perturbation operators. So if you take the derivative of the first order perturbation operator, as we have it in the presence of an electric field, we derived that in one of the last chapters of chapter 2 of the book. If you take the derivative of this operator with respect to a component of the electric field, what we get two operators. We get the corresponding component of the electric dipole moment operator, the electric one, and the nuclear contribution to that. So we can insert that now here, the derivative of the Hamiltonian in our sum over states expression here. So we get for the alpha beta component of the polarizability, we get once here with the alpha component here, and here with the beta component there, and vice versa. You might note that I only used the electric dipole moment for the electrons here in my sum of states expression, so I did not include the nuclear part. Why is that? And secondly, I also dropped this origin dependence. This is just because I dropped it, or is there no? So let's look at one of those transition moments and look in particular at the transition moment which we would get if we sort of had used the nuclear contribution to the electric dipole moment operator. Now this operator, being the nuclear part, only acts on nuclear coordinates, but these wave functions, because we're in the Born-Oppenheimer approximation, these wave functions depend only on electronic coordinates. So I can move the operator out of the integral because it's not the same variables. And so what we end up with an overlap integral between the electronic ground state and an excited electronic state, and those states are orthogonal, so this is 0. So therefore, there is no contribution from the nuclear part of the electric dipole moment operator. Later on, in chapter 8 of the book, we'll come back to that, because there we will look at wave functions which are not just only electronic wave functions, but also nuclear wave functions. There the story will be different, of course. Then. Now, what about the origin dependence? Here the origin depends of the operator. If we insert the expression for the electric dipole moment here, operator, here we have the part which depends on the positions of all the electrons, and here's the part which depends on the origin. And again, in the origin, this is a fixed point in space, so this is not a variable, so of course we can take it out of the integral then. That's what I've done here, and we end up again with the overlap integral between the electronic ground state and one of the excited electronic states, and that this overlap integral is still 0, so the transition moments over the electric dipole moment operator do not depend on the origin, in contrast to, for example, the expectation value in 4 charged systems. So this was the first approach. Now let's look at the second approach. In the second approach, we define a component of the polarizability as the first derivative of a field-dependent component of the electric dipole moment. Here we have a field-dependent component of the electric dipole moment. It's field-dependent because our wave function is not field-dependent. Now we looked at these kind of field-dependent expectation values also in chapter 3 in what we called response theory. And there we actually expanded these field-dependent expectation value of an operator, and we actually concentrated on the dipole moment operator also there in a series where the first term, of course, would be the permanent dipole moment, and then we would get correction to that, and those corrections contained the response functions. And the term linear in the field would include the linear response function, and the term quadratic in the field would include the quadratic response function. So if you now take the derivative of this field-dependent component of the dipole moment with respect to one component of the field and evaluate the derivative as 0 field strength, we exactly get the linear response function. And since we are here looking at a constant electric field, it's the static value of the linear response function. Where we have now here 2 dipole moment operators, and the first one, that's our operator which comes from the component of the dipole moment, and the second operator together with the minus sign comes from the perturbation operator, the perturbation, the interaction of our systems with an external electric field, which is minus the dipole moment operator times the electric field, so that's where the minus sign comes from. You also could sort of take an intermediate step, where we have not yet inserted the response function, but look just on the next term, where the term which is linear, of course, includes then first order correction to the wave function, either in the ket or in the bra. And if we take that derivative, then we get for the polarizability these kind of matrix elements, these kind of integrals where we have the unperturbed wave function, and we have then the derivative of the first order correction to the wave function with respect to component of the electric field, and again evaluate electric fields. Now from these expressions we can sort of apply, we will apply them later on in the third part of the book, where we look at approximate expressions for wave functions. So we will look at derivatives of approximate expression for field-dependent wave functions. But we also can go back to our perturbation theory, because we have expressions for first order correction to the wave function. And if we do that and then take the derivative, remember that the first order correction perturbation theory for the wave function looks like this. We have derived that in somewhere in chapter 3. If we insert this one here, then we actually get back to the same sum of the states expression which we had before, derived by taking the second derivative of the second order correction to the energy.